Perfect. Thank you very much. Thank you to the organizer, first of all, for having me at this very exciting meeting. I'm Matteo Bianconi from the University of Birmingham. And also thanks to Konghyao for introducing the exciting topic of the splashback radius in galaxy clusters. Before going into further details, I would also like to highlight my collaborators in this project. From Birmingham, talented PhD student Riccardo, and the core of the LoCuSS team, also in Birmingham, Graham and Sean. Then we have Chris in Chile, Alexis in Finland, and Arif in Canada. So quickly again, this is just to sort of reintroduce and to reiterate the property of the splashback radius. This is a very simple snapshot showing the trajectories of infalling galaxies from a numerical simulation into a forming massive galaxy cluster as a function of time on the x-axis and as a function of their cluster-centric distance on the y-axis. So you can see here the dramatic effect that the cluster has on its surroundings, effectively capturing whatever it's in its close proximity, and not even that close, especially at high redshift, where we see the reach of its gravitational pull. This effectively results into a steady stream of objects infalling into the cluster potential. If anything, the accretion rate might even pick up at slightly low redshift. But also a clear and interesting feature that you might distinguish in this plot is corresponding to the first apocenter of this orbit's trajectory. So imagine a galaxy infalling through the cluster potential, and the first apocenter is effectively the furthermost point reached from the galaxy itself before turning back and falling back into the cluster potential. This has been used as or suggested as a fairly natural way of defining what can be considered effectively the collapsed part of the halo and what is sort of outside and not yet captured by the cluster. And this indeed is the key definition of the splashback radius. So there's been quite a lot of activity on the sort of characterizing this feature, in particularly driven by extensive work from theory on characterizing this radius and sort of like trying to discern its properties according to the dynamical state of the cluster, as we saw in Kong's talk as well. For us, dealing more with observation, what we are looking for effectively, if we assume, if we imagine the density profile of these clusters, the splashback feature for us would appear effective as a dip corresponding to the outermost shell where the cluster members would reside. And so there's been quite some effort also from observation trying to effectively detect this feature by using different methods and different cluster samples that we'll see more later on. What we're trying to see today is whether we can effectively, as from the simulation side, we can use this splashback radius to also from simulation disentangle and understand more about the cluster formation history and their dynamical state, and whether we can bridge between, for instance, more classical proxies of the dynamical state of clusters, such as the exact properties, morphologies, and so on, and this new tool that we have. To do so, we resort to the LoCuSS survey in particular in this study. LoCuSS survey is an extensive multi-wavelength survey covering some of the most massive clusters below redshift of 0.3, 30 in particular. It's multi-wavelength in that it covers all these objects, as you can see in this sort of sketch on the right. These clusters from the X-ray all the way down to far infrared continuously. Hence, we can really nicely sample all the different physical processes that are going on in these clusters, both in the cluster, so affecting the entire cluster as a system, but also its cluster members, which are consistently selected using the extensive spectroscopic coverage that we have in LoCuSS, which results effectively into quite a substantial sample of galaxies with a mass selected, effectively, sample of spectroscopically conferred cluster members. To see more visually how our cluster members sort of look like, we see the typical phase space diagram here on the left-hand side plot. where we see the cluster-centric distance of our confirmed member plotted with respect to their peculiar velocity as a function of the cluster velocity dispersion in this case. So this is the entire sample of galaxies that we are using for this study. And we can appreciate, first of all, how our cluster members follow the cluster halos and the dark matter halo quite nicely in the typical trumpet shape that we might expect for the sort of collapsed part of the clusters. In addition, we can see also the nice extent of our spectroscopic coverage, reaching effectively 3 times the R200, which is well over the distances we expect for the location of the splashback radius. So we're quite confident we are able to sample the area of interest for us. In addition, thanks to the multi-wavelength set of observation, we can resort to a significant amount of studies that sort of classified our clusters according to their dynamical state using several different proxies, being the central entropy or the morphology of the X-ray emission, as I said before. So looking for, or effectively telling us whether any of these clusters has recently gone through a major merger, for instance, or in any case, if their sort of dynamic is more disturbed. At the same time, thanks to the extensive XMM coverage, we also are able to detect the presence of substructure in the surroundings of these clusters. And in particular, we will use a sample of infalling groups that have been recently discovered around our clusters, and see whether the presence of these objects have any influence on the properties of the cluster themselves. So some results here, you can see on the left-hand side, plot in particular the projected luminosity profile of our total cluster samples. I think that more clearly, if you look at the bottom panel where we see the slope of this profile, we can clearly see the emergence already of a splashback light type feature that is consistently present in our dataset, consistently because also it appears the same location when we consider, or when we select among our clusters, the one that do show a more sort of quite recent histories. This doesn't happen, for instance, when we consider, or where we do the same exercises for clusters that are more disturbed. This is a very simple and two-dimensional effective profile, or projected profile of our clusters. Same we can do by selecting clusters with and without infalling groups, again, showing quite clearly presence of a splashback light type feature. Already you can see that, for instance, in clusters without infalling groups, this feature appears to occur at slightly lower distance, cluster-centric distances, with respect to clusters that have infalling groups. And so to further characterize and have a bit more a quantitative grasp of what's happening, we resorted for these 3 samples, so cluster with and without infalling group, and separately for the total cluster sample, we resorted to model fitting using the prototypical model proposed by Diemer and Kratz of 2014, associating an inasto type profile for the collapsed part of the halo, a power law for what is considered outside of the clusters, and a transition term that allows for the presence of the splashback feature. And we can report that we are successfully fitting the total cluster sample and the 2 cases for with and without infalling groups with this model, so confirming the presence of a splashback feature, also thanks to the Bayesian framework that we are using through the software CP-Nest that allows us to classify models allowing for these transitions as more descriptive of the data with respect to models that are sort of excised of the transition. In this plot, we see a sort of a collection of the most recent results from the observational side on the detection of the splashback radius. We see here on the x-axis as a function of redshift according to the different datasets used, and on the y-axis the splashback radius plotted as normalized by the R200M in this case of the sample used. First of all, we can see our 2 data points. So again, we retrieve, even through model fitting, a significant difference between cluster with and without infalling groups. It is worth noting that our error bars in this plot encompass the 3 sigma level compared to the other results that are only limited to 1 sigma. This is one of the main advantages of using spectroscopically confirmed cluster members that allow us to significantly reduce the contribution of interlopers, which are indeed recently being suggested also as the responsible for some of the earlier results, observational results on the detection of the splashback feature, which are understood to be an underestimation of what is the true location of the splashback radius. We attempted also a connection or a comparison with what simulation might tell us in terms of the location of the splashback feature according to the accretion rate of galaxy clusters. This is rather challenging given that the timescales, doing a one-to-one comparison between different between observation and simulation is challenging due to the timescales considered and the difficulty of sampling the entirety of the accretion rate in observations. Nevertheless, simulation seems to suggest that halos that are creating significant amount of matter do show a contraction of the splashback radius. In this case, we see that the contraction for us occurs for clusters that do not show infalling groups in their surroundings. This doesn't mean that our results are necessarily at odds with the simulations. We might just be sampling slightly different timescales. What I think is a really good takeaway to have from this is that this LoCuSS dataset has allowed us to sort of attempt a precursor study of what will be the next step into cluster science, thanks to new facilities that will come online soon. Just imagine the synergy between, for instance, Foremost and eROSITA, increasing the census of known galaxy cluster and cluster members manifold. And so it will be a very exciting time for cluster science. I want to reiterate that this is the first study that confirmed the location, the detection of the splashback feature using spectroscopically confirmed cluster members, and that we see evidences of the relation between the dynamical state of the cluster and potentially its accretion history with the splashback location. And so it's very exciting to see effectively how these massively different scales are talking to one another. And I think I'm done with time.